Hello, and welcome to this lesson on the Introduction to Calculus. We're talking about differentiation, and specifically the definition of the derivative. To begin with, let's take a look at some function. Just assume we have some function here, f of x, and maybe the curve looks something like this. An important part of this is that we require a curve that is what technically we call smooth. Smooth means that you can find the limit anywhere on that curve. So if you want to do this business of what we're going to call differentiation or taking a derivative, we require that you can take the limit at every point. So if you don't recall what a limit is, make sure you go back and review that. To begin with, let's look at a couple points here. We have these two yellow points, and let's say that we are interested in finding the slope between these 2 points. Now, why would we do that? Well, calculus is actually, at least in terms of differentiation, is all about finding how things change. We're interested in the subject of change, and this is kind of a new concept that calculus brings to the table. Not only just a change, as you may have done when talking about, say, velocity or average velocity, we're interested in something called instantaneous change, meaning how a curve changes at every point. Well, to begin with, we're going to start with something simpler, and this actually relates to the concept of like an average velocity. So we're interested in the slope between these 2 points because that's telling us kind of the rate at which this function is increasing or decreasing if the curve goes down with respect to the change in the x value on our horizontal axis. So in order to do that, let's label a little bit more on this curve. And let's call this first point x naught, and this other point x naught plus some amount, and let's call that delta x. Now it doesn't matter what delta x is, and as we'll see, we're going to make it arbitrarily small actually. But to begin with, let's just assume it's some number. And correspondingly, if we wanted to find the value of those functions at those points, obviously we would have f of x naught and f of x naught plus delta x. So those are the values of the independent and dependent variables at those 2 points. So I said that we're interested in finding the slope that goes through these 2 points. So let's draw a line. And this line has a special name. It's actually called a secant line, and you might have recalled the name secant if you studied trigonometry. Sort of a related concept, but it's a bit convoluted in exactly the relation there. But for now, let's just call it the secant line, a line that passes through 2 points of a curve. And so to find the slope of the secant line, what are we going to do? Well, that's pretty easy, right? We just want the rise over the run, just like you calculate the slope of any line. And so the rise, how much it's increasing, we're just going to find the difference between f of x0, x naught, plus delta x. And that would be minus f of x0, right? And then we're going to divide by the run. Right? So then we're going to take x0 plus delta x, and then we would subtract x0. Well, clearly these x0s are just going away, and we just have this value divided by delta x. All right. But actually what we're interested in calculus is finding the slope of what's called the tangent line. And the tangent line means a point where, a line rather, that passes through a single point. So a secant line passes through 2 points, we want a tangent line which will pass through just one point. So maybe we're interested in this point here. And so essentially I want to find a line that just kisses the curve right there. Now it's okay, eventually the curve might pass through that tangent line again. But what's important is that our line is defined by just passing through that single point as you get arbitrarily close to the point of interest. All right. So how are we going to do that? Well, I kind of hinted at it earlier. The idea is we're going to change our delta x here by making it smaller and smaller and smaller, such that this second point is getting closer and closer to our original point, and therefore the secant line will be getting closer and closer to what we would hope to be our tangent line. All right, so we're going to set this up by finding the slope of the tangent line by making delta x get arbitrarily small. So this might remind you of the concept of limits, and that's exactly what we need to use in order to calculate the slope of a tangent line. And this again is why we require that our curve is smooth. We need to be able to find a limit everywhere on this curve. So this is what we would write. The limit as delta x approaches 0 becomes arbitrarily small of our original expression for the slope of the secant line. This might be a bit surprising to you because we have delta x in the denominator and this thing is going towards 0. And this actually caused a lot of controversy when calculus was first being discovered, or invented if you'd like. People didn't really feel very comfortable with this notion. It seems as though we're dividing by 0. And it took quite a long time before this whole idea was made rigorous. But it works, and this is the amazing thing that people had to grapple with. Delta x is actually not becoming 0, but it's getting infinitesimally close to a 0 value. And we're going to do an example to see how this actually works out, and we don't run into any problems at all. Okay, so let's set this up. This is the slope of the tangent line specifically at a point that we have called x0 comma delta f, f of x0. Okay, so this is slope of our tangent line at this point. And this also has another name, so this is the definition of the derivative at a point. Okay. Note, however, that we didn't have to define this at any specific point. We could have done this at any point of x, so we're going to actually remove this. And we're just we'll get rid of all of the x naughts and just make them x's. So this is true now for any value of x. So we call this the definition of the derivative. All right, let's take a look at an example. Okay, let's consider this quadratic equation. This function is 2x squared plus 3. So we're interested in finding the derivative of this function. I should say one more thing about what this is actually telling us, because remember, when we had the x naughts here, it was defining the slope of the tangent line at a specific point on that curve. But because we're just talking about x in general, we're talking about something much more general. We're talking about the slopes of the tangent lines everywhere for every point on the curve. So this is a new function that essentially lists all of the slopes of all of the tangent lines for all of the points on that curve. And it has several different ways of writing this expression. You would say this thing equals, and we might label it as f prime of x. That's one way of writing it. You'll also see dy dx. That's how it's pronounced, dy dx. So you would say f of prime of x equals this, or dy dx equals this. And that means the same thing. So we're looking for a new function. It's not going to be just a slope. It's going to be a function describing all of the slopes. So we're interested in finding this f prime of x, the derivative. All right, we're going to use our definition here. We take the limit as delta x approaches 0. And we write our original function, but wherever we have x, we're going to write x plus delta x, so 2 times x plus delta x, all squared, plus 3. And then we're going to subtract the original function, so we're subtracting 2x squared, and we also have to subtract the 3. Oops. Okay, and then all of that is divided by delta x. Okay, let's expand that. Don't forget to write out the limit every single line that you still have it with you. So now we have 2x squared plus, that's going to give us 4x times delta x plus 2 and then delta x squared. Okay, and then we see the plus 3 and the minus 3, those already cancel each other out, and then we have minus 2x squared here. Okay, and then we still have our delta x in the denominator. We have some other nice cancellations. 2x squared, I'm sorry, yes, 2x squared will cancel out. All right. We still have the limit, don't forget to write it. Delta x approaches 0. 4x times delta x plus 2 times delta x squared. Okay, and then all over delta x. Aha, so now we see that our delta x's can cancel out. We can get rid of one of them here. And we still have the limit, but now we have just 4x plus 2 times delta x. And now we can evaluate the limit. And we don't have any problem because there's no delta x in the denominator. So this delta x will go to 0, and all that we have left is 4x. So this tells us basically instructions for finding the slope of a tangent line at any point on the curve. If I wanted to find the slope of, say, the tangent line when x equals, let's say, 2, so f prime of 2, this is telling me the slope of the tangent line on the curve f of x, this parabola, when x equals 2. Well, I just simply put in the value of 2 for x, and so I would get 8. The slope of that tangent line at that point would be 8, and that is actually the correct answer. All right, that's it for this lesson.